Hi, I am going to model an alpha decay process, and I'm going to do that by using this isotope fluorine-20. Just so you know, fluorine-20 and elements with less than 82 protons do not generally go through alpha decay. However, for the purposes of this video, I wanted to make things simple. I didn't want to have to build a giant element, and so we're going to go ahead and model the process of alpha decay with a lighter isotope, even though in real life this lighter isotope would not actually undergo something like alpha decay. All right, so this isotope that I built is fluorine-20, and this process that I'm doing would work for any radioactive isotope that would undergo alpha decay. So this one in particular I just built is fluorine-20. So it's fluorine because it has 9 protons in its nucleus. So you can count all the plus signs and you can see that there are 9 of them. And it's that 20 is its mass number. So that means that collectively there are 20 protons and neutrons. That number adds up to 20. So there's 20 particles in its nucleus. And we call it a parent isotope because it is going to go through decay and produce an offspring. And that offspring is what we call a daughter isotope. And our parent isotope is radioactive. And all that means is it's unstable. So its nucleus, for whatever reason, maybe there's just too many protons, maybe there's too many neutrons, but it's just crumbly, it's not stable, and so it's pushing out. That strong nuclear force is having a hard time counterbalancing the repulsion of those protons, and so it's just trying to correct that instability, and it's going to do that through alpha decay. So what alpha decay is that this nucleus is literally going to push out a piece. So that piece kind of shoots out of there, and the piece that it shoots out is made of 2 protons and 2 neutrons. So 2 protons, 2 neutrons. And that little piece, we call that an alpha particle. An alpha particle is a type of radiation. So whenever you hear about radiation, one type of radiation is actually alpha particles. So those alpha particles that shoot out actually can be kind of dangerous because they're moving at high speed when they shoot out of that nucleus. So, they're like tiny bullets. So anyway, this type of radiation happens to be an alpha particle made of 2 protons and 2 neutrons. And you might notice that this thing now is its own little nucleus. And those 2 protons and those 2 neutrons, if you add them together, you get a mass of 4. And 2 of those are protons. And if you look up what has 2 protons on your periodic table, you'll see that that's helium. So your alpha particle is a helium nucleus. It is eventually going to pick up a couple of electrons from just out in the world and end up just being a helium. So there you go. So what makes it dangerous is not that it's helium, it's that it shoots out of there at pretty high speed, and it can tear through your DNA, break bonds in your DNA if this is happening in your body, and cause mutations, things like that. All right, so let's look at what happened to our fluorine over here, because it's not fluorine anymore. So you can see that it has lost pieces from its nucleus. In fact, it lost 4 total pieces. So the mass of this thing is going to go down to 16 because we just lost 4 pieces. 2 of those were protons, so we have to take 2 protons away, so now we only have 7 protons. And then that means that this is no longer fluorine. It has 7 protons, so if you look on your periodic table, you'll see that it has become nitrogen. And it is no longer a parent isotope. It is now what we call a daughter isotope. So the parent became the daughter by spitting out a little piece. So it's actually transformed into a new element, a new isotope. Now, if we were to write the equation for this decay, right? Because we can represent all of this with an equation. Well, we started with fluorine with 20 particles, 9 of which were protons. That fluorine is going to undergo a process, so the arrow represents that it's going to undergo a process. In this case, it's undergoing alpha decay. And as it undergoes alpha decay, it is going to, again, give off alpha particles. So the alpha particle that it gives off has 4 total pieces. 2 of them are protons. So it's a helium nucleus. So our alpha particle is actually a helium nucleus. And then what gets left behind is 4 less than that 20. So 16 pieces less. 9 of those were protons. It just lost 2. So now it has 7 protons. And then if you look that up, of course, that's a nitrogen. So what we have is this process where that everything that we started with, right, the protons and the neutrons, all they did was split into 2 groups, and those are the 2 groups. So when you look at the numbers, the top number on the left, 20, on the left side of the arrow, the top number should still add up to 20, right? Sorry about that, I crossed out my 16. And the bottom number, we had 9 protons, and that should still add up to 9 here on the bottom. So all that happened was the fluorine split into those 2 pieces. This is your alpha particle, right? So there's your radiation type. And of course, this is your daughter. And that's alpha decay.